So when you hear the word serotonin, your mind probably jumps straight to one thing, the happy chemical, right? Well, it turns out that's just scratching the surface. Today, we're going to go way beyond that simple idea and look at what serotonin really does. Think of it less like a mood booster and more like a master sculptor, physically reshaping the connections inside your brain with every single thing you experience.
And that brings us to the big question that's going to guide us through this whole thing. How does one single experience, learning a new skill, feeling a powerful emotion, actually leave a physical mark on your brain? The answer is all about how our neural wiring can change. And believe me, serotonin is one of the key players holding the chisel.
Okay, so to get to that answer, we have to start with a really fundamental concept. Our brains are not set in stone. Not at all. They are constantly, and I mean constantly, rewiring themselves based on everything we do and everything we experience. This is it. This is the very essence of how we learn, how we adapt, and how we become who we are. Now, the fancy term for this process is synaptic plasticity. But don't let the name intimidate you. The idea is actually pretty simple. Imagine your brain is this huge, complex network of phone lines, and these lines are the synapses connecting everything. Well, plasticity is just the ability to make the connections on the really busy lines way stronger and clearer, while letting the connections on the lines nobody's using just fade away. It's the biological bedrock of all learning and memory. This whole idea was captured beautifully way back in 1949 with this one elegant phrase you've probably heard before: neurons that fire together, wire together. It's so simple, right? It just means that when two brain cells are active at the same time, the connection between them, that synapse, gets stronger. That's it. That's how our brain forms associations. And this process basically follows two main rules. On one side, you have long-term potentiation, or LTP. That's the wiring together part. When you have frequent, high-powered signals between neurons, that connection gets stronger. It's like turning up the volume on their conversation. And on the other side, you've got long-term depression, or LTD. This is your use it or lose it rule. Less frequent signals actually weaken the connection, like turning the volume down. Together, these two processes are how the brain constantly refines its own circuits.
So where does serotonin come into all this? Well, it's not just another message bouncing around. Serotonin is what we call a neuromodulator. It doesn't just send a message. It fundamentally changes how messages are sent. It's the sculptor that comes in and decides which of these connections get carved into stone and which ones get smoothed over and forgotten.
And it does this in two really cool ways. First, there's a plastic effect. That's when serotonin itself just directly causes a connection to get stronger or weaker. Simple enough. But the second one, the metaplastic effect, this is where it gets really powerful. Here, serotonin changes the rules of the game. It's like a foreman on a construction site who says, "All right, team, for the next hour, anything you build is permanent." Serotonin isn't doing the work itself. It's making the synapse more or less likely to change based on whatever happens next. It's literally priming the brain to learn.
So how can one chemical be so versatile? Because it doesn't just have one tool in its belt. Serotonin works through a whole family of different receptors. You can see some of the key ones here. You can think of each one as a different kind of chisel. This is what allows serotonin to do very different, very specific jobs depending on which part of the brain it's in. All right, let's see this sculptor in action. We're going to take a quick tour of the brain, and our first stop is the hippocampus. This is basically the headquarters for forming new declarative memories. You know, the what, where, and when of your entire life. Now, inside the hippocampus, information follows a really well-known path. It comes in, gets processed, and then travels along this critical connection point called the Schaffer collateral pathway. This is the link between an area called CA3 and another called CA1. And it's right there, at that connection, that a whole lot of the memory-making magic happens. Okay, now look at what serotonin does here. This is wild. This table, which is based on the research, tells a fascinating story. If you activate the 5-HT1A receptor, it actually weakens the connection. It causes LTD, which can get in the way of forming a memory. But if you activate the 5-HT4 or 5-HT7 receptors, you get the complete opposite effect. It strengthens the connection through LTP, which actually enhances memory. So let that sink in for a second. The crucial point here is that in the exact same part of the brain, serotonin can act as both a brake and an accelerator for making memories. It all just depends on which receptor, which one of its tools, it decides to use.
We are a long, long way from a simple, happy chemical now.
Okay, so serotonin can hit the brakes or the gas on memory. But does it play by those same rules everywhere else in the brain? Well, let's find out. Let's hop over to our next stop on the tour, the amygdala. This is the brain's emotion hub, and it's absolutely critical for processing things like fear and deciding how we respond to threats.
The amygdala also has its own key pathways. Sensory info, what you see, what you hear, flows into a part called the basolateral amygdala, or BLAC. The BLAC is the part that figures out, hey, is this important? Is this scary? And then it relays that info to the central amygdala, which is what pulls the fire alarm and triggers the body's fear response. This is where fear learning gets locked in.
So, what's serotonin doing here? Check this out. The 5-HT2A receptor strengthens connections, which totally makes sense for learning what to be afraid of. But look at that top row. The 5-HT2A receptor, the very same one that weakened connections in the hippocampus, now it strengthens connections here in the amygdala, helping to fine-tune our aversive memories.
And that right there brings us to the key puzzle. You have to be asking yourself, hold on a second, didn't that exact same receptor do the complete opposite thing, just one brain region over? And the answer is yes. Yes, it absolutely did. And that stunning contradiction is the single most important takeaway from this entire explainer. So this brings us to our final section. We're going to put all these pieces together and finally understand how one single chemical can have so many different and sometimes completely opposite jobs to do.
Let's just put it right here, side by side, so it's crystal clear. In the hippocampus, our memory center, hitting the 5-HT1A receptor weakens connections. But in the amygdala, our emotion center, hitting that very same receptor strengthens them. It's like serotonin has a split personality, and its identity is defined entirely by where it is. So here's the bottom line. It's not the chemical, it's the context. The effect of serotonin isn't some property of the molecule itself. It's all determined by the neighborhood it's in, the type of neuron it's talking to, and the specific receptor it happens to bind to. It's an incredibly sophisticated context-aware system for sculpting the very circuits of our brain.
And that leaves us with one final thought to chew on. We started by pushing back on the simple idea of a happy chemical. And now we see serotonin for what it is, a master sculptor with a highly specialized toolkit, doing totally different jobs in different workshops all over the brain. So knowing that its role is this incredibly nuanced, how might this change the way we approach everything from brain health to the future of medicine?